Steinhauer here. Welcome back. Continue our discussion of cosmology and Big Bang and some of the biggest questions that can be asked in the universe. And we're going to take a brief hop to chapter 27, which is an extremely interesting chapter on active galaxies, quasars, and supermassive black holes. We're not going to spend much time in this chapter, unfortunately, because we don't have much time left in the semester. But if you are interested in active galaxies, quasars, and or supermassive black holes, and let's be honest, who isn't? I encourage you to read this one on your own because there's a lot of really interesting stuff in there. We are going to focus, though, on the section of chapter 27 that talks about dark matter, because it's going to be relevant to all of the rest of the things that we talk about this semester. So let's just remind ourselves and set ourselves back in the context of dark matter. You might remember in our chapter on the Milky Way, we measured the mass of the galaxy. We put it on a cosmic scale. And you might remember we did that by measuring the distance between the sun and the center of the galaxy and measuring how fast the sun was orbiting the galaxy at that distance. And there's a fairly simple formula which takes those two numbers as input and outputs the entire mass of the galaxy that is within our orbit. And when we did that, we got a number that was about 10 to the 11. 100 billion solar masses. But again, this is a formula that cannot just be used to measure the mass of the entire galaxy or even the mass of the galaxy within our orbit. It can be used to map out the spatial distribution of matter within the galaxy. If you have a star at any distance, and you can measure the distance between that star and the center of the galaxy, and you can measure that star's orbital velocity, you can get the mass inside of this orbit. And you can even do this for stars that are further out and get the mass inside this orbit. So not only do you get the total mass by taking stars that are extremely far out in the galaxy, but you can get how that matter is distributed through the universe, through the galaxy. And in fact, when you do this for objects that are at the far edges of the galaxy, you get a total mass of the galaxy that's about an order of magnitude larger than the mass that is in our orbit. It's on the order of 10 to the 12 solar masses, a trillion solar masses, which is a factor of 10, again, above what's inside our own solar orbit. So, and this is another diagram that we saw from before. So there's two problems here, right? One is there's lots of matter that we can't see, right? The inferred, when we get. So there's two basic problems. The first one is we're detecting a lot of matter that isn't there. When we actually count up all of the mass that we can see, all the stars, all of the gas and dust, all of the nebulas, all of the black holes, even everything that we can infer its presence, we only get to about 10 to 15% of the mass that we need to explain the velocities of stars in the galaxy. So that's a problem. The other problem is it seems that there's more mass even outside the visible extent of the galaxy itself, right? 40,000 light years is about where we see the galaxy itself end. There aren't many stars out beyond 40,000 light years. It's pretty much just empty space out there, it looks like. And so remember, we would expect that once you're outside all of the mass of a system, that the light curve would fall, the rotation curve would fall off as a Keplerian, in a Keplerian way, like the solar system does. The solar system has all of the mass at the center, and we see its rotation curve fall off like this. We would expect, once we get outside all of the mass of the Milky Way, that our rotation curve would also fall off like that for the smattering of things that are out there. Not only does it not fall off, it actually goes up out there. What does this imply? It implies that there's a lot of mass out there, not only that we're not seeing, but beyond the visible extent of the galaxy that we see it as a whole. So those are the two problems. Lots of mass that we're inferring that we're not seeing, and it's situated it's distributed in a way that's very different than the visible matter is distributed. This dark matter is behaving weirdly. In fact, if you were to draw a true diagram of what the galaxy is, what is the galaxy? It might look something like this. So here is the traditional galaxy in the center. You've got the disk and the bulge and all these halo objects and globular clusters. This is what we would have normally talked about being the galaxy itself. But again, this is only about 10 to 15% of the mass of the galaxy. The galaxy itself is really the dark matter. And the dark matter seems to be distributed fairly uniformly in a spherical distribution around the visible matter, but extending much further out than the visible matter seems to extend. And so when you talk about the galaxy itself, what are you talking about? Well, again, this is the stuff that we see, the stuff that we normally think about is actually a very small percent. The galaxy is really the dark matter. That's 85 to 90% of the mass of the galaxy. It's in this halo. And we don't even know what it is yet. It's kind of embarrassing. It's 2020. We don't know what 85% of the galaxy is made of. So that's a problem. But it's interesting that the distribution is different than the distribution of luminous matter. It extends much further out than the galaxy seems to, and there's a lot of it out there. Okay, the question is the Milky Way unusual in that? Or do all galaxies seem to show this? And here I just show an example of 4 different other galaxies and their rotation curves. We can measure these rotation curves for lots of other galaxies as well. And what do we see? Well, we see rotation curves that look very similar to the Milky Way's rotation curve. There's some a period in the center where it gets very, very fast, and then it kind of levels off, and you get these roughly flat rotation curves for all of these different galaxies that extend, in some cases, much further from the center than we were even able to measure for the Milky Way. Remember, the Milky Way stopped at about 40,000 light years. These extend out to 50, 100, sometimes even 150,000 light years. We can still measure these rotation curves, and they're fairly flat all the way out there. There's some wiggles, but they're not changing drastically up and down as you move outwards in these galaxies. So all spiral galaxies seem to have these flat rotation curves, and these flat rotation curves indicate large amounts of dark matter. The Milky Way is not unusual. We see lots of other galaxies. In fact, every other galaxy that we see seems to have this same property, where most of the mass is in dark matter, and it's revealed itself by these rotation curves. Okay, now maybe we just don't understand how gravity works. Let's try to measure the mass of something in a fundamentally different way, besides measuring how fast things are moving around other things. Here's a way that we can do it. It turns out, remember the difference between Einstein's theory of general relativity and Newton's laws of gravity was that, according to Einstein, gravity is just bent space-time. And because gravity is just bent space-time, things like photons will also be affected by it. And remember this, you may remember this is how it was actually proved that Einstein was right by measuring the light bending angle around as starlight passed right by the sun during a total solar eclipse. Well, it turns out that this property of mass bending light can be used to measure the mass of other things as well. So here you see an example of a galactic cluster, a cluster of galaxies. There's a huge amount of matter there. And what you see is there are background galaxies here, and you're seeing these blue objects here, here, and here, and those aren't members of the cluster. Those are background objects. Those are much further away than the galaxy cluster that we're looking at in the foreground, all those orange objects. And what you see is the light from that galaxy, as you're seeing in this diagram, is bent. So some of it comes straight through, and some of it gets bent. And so it it actually does bend around this galaxy, and we see it actually coming at us from different angles. And so what you're seeing in this diagram is perhaps this galaxy and this galaxy are probably the same galaxy. And that galaxy is actually physically located maybe there in real space, but we're seeing multiple images of it because the light from that galaxy is getting bent in a certain way and being redirected towards us in different directions. And so from the Earth, it looks like this galaxy is both there and there and there. And when we see the galaxies, we actually get 3 images of it, 2 of which are fairly distorted on the outside, and 1 of which is fairly undisturbed going right through the middle. Well, we can take advantage of this. If we know the relative distances, the geometry between us and this galaxy cluster and us and this real galaxy in the background, then we can figure out what angle that light has been bent by, based on what angle this seems to be. And that will tell us how much matter is here and how much space-time is curved and how much mass there must be to make that angle happen. And when we do that, we find, here's another example of it. Look at these beautiful arcs. These are all background galaxies whose light has been bent around this foreground cluster of galaxies, and we're seeing it now in streaks in various ways. Guess what? We get about the same answer. We get about that 90% of the matter, 85 to 90% of the matter in this galaxy cluster also isn't in the form of visible matter, right? We can calculate the total mass by how much these gravitational lensing effects have taken, and we can count up the visible matter. We can say that's a galaxy, it's got a luminosity of this, must have a visible matter equivalent of about this, and guess what? We only get to about 10% of the total mass that we need. And so this isn't something that's just within galaxies. This isn't something that's just a statistical fluke or a lack of understanding of how velocities work. There's something fundamental there, and that's important. Okay, so we're really down to 2 options, and this is how science works, and this is really important because we do have 2 options. One of them is that dark matter really does exist, and we are observing the effects of its gravitational attraction, but there is also the possibility that that's wrong. And it's possible instead that we just don't understand how gravity works completely. And that's an exciting branch to try to follow. So far, nobody has been able to convince the community that their new version of gravity is right, but that doesn't mean that that's not out there waiting for someone to do. And people are working very hard on this. You might imagine if you're the person who figures out how to explain all of this stuff without the need for dark matter. Dark matter is not the ideal option. You might have heard of Occam's razor. Occam's razor says if you've got 2 competing theories that both can explain the data, choose the simpler one. The simpler one is almost always the right one. In this case, it's much simpler and less uncomfortable to choose the option that doesn't require us to not know what 85 to 90% of the universe is. That's a really uncomfortable thing to do. Explain your data by having to invoke the fact that there's all this missing matter out there. So if somebody can come up with a new theory of gravity that explains all of this stuff, then not only are they famous and have won a Nobel Prize, but they have done away with this uncomfortable notion of dark matter. However, nobody's been able to do that yet. And so now we're left with, well, like Sherlock Holmes said, if you've ruled out all the other possibilities, then whatever's left, however unlikely, must be the actual thing. And that's sort of where we are now with dark matter. Okay, we'll come back in the next video and think about the options of if there is dark matter, what that dark matter is and what it might be made of. We'll see you then.